Okay, our next speaker will be Professor Peter Stone. Peter is the founder and director of Learning Agent Research Group at UT Austin, as well as Associate Department Chair and Director of Texas Robotics. His main research interest in AI is understanding how we can best create complete intelligent agent. And thank you for taking time out of your schedule for coaching RoboCup. And today he's going to talk about human-in-the-loop learning for robot navigation and task learning from implicit human feedback. Let's welcome Peter.
Okay. Thank you very much for the invitation. And I'm sorry I can't be there in person. I was hoping to. I'm actually relatively nearby. I'm in Eindhoven, which would only be an hour and a 15-minute train ride if I were near the central station, and so were you. But all in all, it would have taken too long for me to get there and back and still be here for things I need to be at. I'm here in Eindhoven for RoboCup. And I have a bunch of things I could say about this fun topic on task specification. And so, but I'm going to take advantage of the fact that I'm here at RoboCup to sort of show you some things that have happened just this morning that are relevant to this. I will say, Hadas, I think probably the reason you put preferences up on your slide at the end was that I'm going to say some things about preferences at the end. So thanks for setting that up for me. Yeah, good thinking. So I do well. Yeah. So actually, I'll just jump to I am here at RoboCup, and RoboCup is usually started as robot soccer, where the task specification in some ways is quite simple. It's just win the game. But it actually gets much more complex than that when you sort of drill down. There's score the next goal, or there's defend against that kind of a shot. There's all kinds of different task specifications that can be given. I'm not actually going to talk about soccer. I have a team in the robot soccer competition, but also in this video that I have up here in the RoboCup at home competition. And this is for those of you who aren't familiar, it's something where you have to have a robot that's that does sort of domestic tasks. And actually I won't. Yeah. So this is our robot, and it was in a task called general purpose service robots, where the robot has to come into the room and then listen to a person just tell it its task in natural language. But I think you maybe be able to hear it here. Okay, we can't really hear the audio. That's what I thought. So I'm going to turn off the audio. And I'll just tell you what the task was. The person there said, "Tell me how many standing persons are in the office." And oops, and the video jumped back. So the person said, "Yeah, tell me how many standing persons are in the office." The robot repeated back, "Is that what you did you ask me to go tell me how many standing persons are in the office?" The referee in the red shirt said yes. And then the robot needed to navigate back into the office and look there around where there are two standing people and one person sitting. Had to look around, and it didn't know that this was the command it was going to be given. There's a large space of possible commands that the robot could be given, and it has to do as many tasks as it can in a 5-minute period. And so here it did. It looked around. It's now going to go back and report back to the referee. And in fact, in this case, it didn't quite get it right. It came back and said there was one person standing, and it said it in natural language as well. And so this was the task specification here, though, is just plain natural language. And the other 4 tasks we were given over 2 possible runs are shown here. Tell me what is the heaviest fruit on the desk. So it had to go navigate, see that there was an apple and a lemon, know that the apple was heavier. Then it was told to fetch a drink from the shelf and place it on the TV table, or tell the gesture of the person at the kitchen counter to the person at the shelf. And then in that case, there was a person standing, raising his right arm. And then also tell me what's the heaviest object on the kitchen cabinet. So this is sort of to me, the kind of task specification we've always dreamt of being able to use in AI, just plain natural language in a huge space of possible tasks. And the robot needs to not only understand it in natural language, it needs to do online planning, execute the task, and then come back and report in natural language. And so this isn't actually at all what I was planning to talk with you about, but I was thinking about the topic of this workshop as this was happening this morning, and thought I'd share that with you. But going back to what I did plan to say, and sort of in the interest of time, I'll skip through some things. Usually in a talk like this, I'd tell you all the great things that are oops, but yeah, that are happening here at UT Austin. We've got we have an AI institute and a beautiful new space for Texas robotics. I tell you about my overall research question, which you can find in some of the other talks I have online, but it's all about multi-agent systems, reinforcement learning, and robotics. But for this talk, I'm sort of actually going to give a brief summary of a bunch of different lines of work, but reframing them in the context of how the tasks are specified. And in contrast to sort of the sort of most run of the mill way, or the most traditional way, at least in reinforcement learning, of just giving a scalar reward, which would be akin to, in the robot soccer case, just saying win the game and no other information. When it comes to human in the loop learning, though, an area that I've been involved in for now 15 years or so, it gets much more interesting than that. It's not just that there's a reward, a scalar reward signal, but there can also be input from a person in different forms. And my first sort of foray into this, which I'm not going to talk about in detail, but was the Tamer system that was introduced by Brad Knox in his PhD thesis, which gave the ability for a person to give the sort of a replacement for reward in a reinforcement learning system. And so it wasn't just this environmental signal, but rather a person being able to say good job or bad job. And in some sense, the task was specified in that way. And this was extended to, it was first done in the Tetris setting. I'll show you an example of that, extended to learning from pixels about a decade later. And then also we've done some work on sort of a related modality of human in the loop learning of imitation from observation, where the task specification is just get as close as possible as to the task that you're observing, that a person do. And this was the PhD thesis of Faraz Tarabi more than 5 years ago now. And just to give the sense for those of you who aren't familiar, in sort of our original Tetris system for Tamer, rather than saying what you would traditionally say is like clear as many lines as possible in the game of Tetris, instead there's a person here who can say good job or bad job. The square up in the top left flashes red when a person is saying bad job, and green when the person is saying good job. And the finding, and so this was an alternate, we didn't think of this as a task specification question. We thought of this as sort of an alternate paradigm for reinforcement learning. But in some sense, that's exactly what this was, is a way of specifying the task through human preferences, or in this case, just positive and negative feedback. And the really nice result here was that, even in the first game, which was shown here, I get this, 1 second. Sometimes the video hangs. It was starting to do much better than random in a setting where, using the traditional task specification of just how many lines have you cleared, it would take hundreds of thousands of games to get really good performance. This is a video of what would happen after just 3 games, 3 episodes of a person giving that positive and negative feedback, and it's already playing the game quite effectively. And so what we learned was that Tamer learned much more quickly with this task specification, not in asymptotically, not as well as the autonomous learners that were doing it from the traditional task specification of just 1 point for clearing each line or something like that. But then we did look at how can these be merged, and how can we take this to video input. And in some sense, we didn't name it this in the end, but this was really the first instance of reinforcement learning from human feedback, which is known now as RLHF, and played a big role in the success of ChatGPT, and has inspired a bunch of research, additional research that I'm going to touch on before the end of the talk. And then, as I mentioned, there's also that's when the person is just saying good job or bad job after every action. Then another task specification that's been explored extensively is the imitation learning. That can be learning from demonstrations, where what you get is the actual actions that a robot took at every particular state. The twist on that Faraz, shown here, did in his PhD thesis in collaboration with Garrett Warnell and myself, was that we were doing imitation from just observations, where we didn't know what actions the agent took. We just got to see the sequence of states that they went through. So the same thing, like if you're watching a fitness instructor and they start doing jumping jacks, right? You don't know what motor impulses they sent to their their arms and legs, or what signals from their brain, but you can see what they do and you can try to imitate it just from observation. So we introduced a model-free method, or a model-based method known as behavioral cloning from observations, and a model-free method, generative adversarial imitation from observation, that sort of opened up the space of a task specification of just trying to imitate the sequence of states that are observed over time. What I'm going to dive into a little bit in a little bit more detail is some more recent work than those. Very much in the same vein of these, learning from human feedback. I'm going to talk about some work with Tracy Zhao on human in the loop learning for robot navigation, and this is robot navigation is one of the most sort of long-standing tasks in artificial intelligence. It's get your robot from a particular place to another particular place, and the traditional task specification is just the XY coordinate that you're trying to get to, or the location that you're trying to navigate to. That's the global goal. But of course, this can also be decomposed, into maybe first having you can do path planning and come up with a global path, and then that becomes the task specification of just follow this blue line, follow the path that I have planned. Or you can you can have waypoints along that line, which are the sort of the local navigation targets, and that becomes the task specification for a short period of time in sort of a temporal abstraction kind of setting. And then there's even below that, there is a task specification of the motion commands. Like, I want to accelerate and turn to the left, and that's a task specification for a PID controller. And so there's this task of robot navigation can be decomposed into these different task specifications of motion control, local planning, and global planning. And then and that's even in sort of the business as usual kind of way, but then connecting back to Tamer and invitation from observation. And I apologize again, I'm skipping through like a presentation where I would talk about all the technical details of this to just highlight the task specification aspects, which is where we first of all we were looking at this in the setting of navigation in highly constrained environments. This is actually an aspect of robot navigation that's not completely solved. Like, you can navigation on a road or in a relatively open space is not, I wouldn't say completely solved, but fairly fairly well studied and with very mature technologies. But when you have spaces that are barely bigger than the robot that it has to navigate through, navigation is still quite a challenge. And then, of course, there's also social navigation when you have to navigate with people and dynamic objects. But here we're focusing mainly on the highly constrained environments. And in those settings, classical motion planners that sort of using the paradigm I just showed require a lot of computation, so can slow down the robot. People have been looking at learning-based planners, but they need a lot of training data. And so we were looking for sort of hybrid approaches, and really then task specification ended up playing a really big role. This is, by the way, Shuisu Zhao, who's faculty at George Mason now, has been leading a series of robot competitions for robots navigating through highly constrained spaces. So here you see the robot and the sort of the maze that they have had to navigate through at a series of ICRA conferences. It's called the Barn Challenge. Encourage you to join. It's got a simulator where you can test technologies, and then the ones that do best in the simulator are invited to deploy them on a real robot. But our approach to this kind of a problem we've called adaptive planner parameter learning. And again, without going into the details of all of the different sort of sub approaches here, this slide summarizes the different ways that we've specified the task beyond just get to the global goal or even the local goal. There's teleoperated demonstrations in a method called APPLE-D, adaptive planner parameter learning from demonstrations, where the task is specified first by a person teleoperating the robot through the constrained environment, which gives sort of gives clues on where you need to drive more slowly and more carefully, like through the narrow corridor, and where can you speed up and drive with a little less with a little less care. And then that provides a specification of the task that we use to try to come up with the planner parameters. I'll talk about exactly what that means on the next slide. But then similarly, we've looked at not just demonstrations, at corrective interventions in this video on the top right, where a person doesn't give full teleoperations, but just steps in and corrects the robot when it does something wrong. And we in that work, we specified two different types of interventions. One's where the robot is going to take a wrong path, maybe run into a wall. Those are the ones we call type A interventions. And then or others where it's using a perfectly fine path, but it's moving too slowly, which we called type B. And so again, the task specification here was in some sense, do what you would normally do, except in the cases when I've taken control and said you're doing the wrong thing. And try to learn from that, try to generalize, try to, the specification is in some sense, learn where I would intervene and then drive more like me, but otherwise do what your default policy says. Which is actually quite an interesting task specification, I think, because it depends on what the default policy is. And then there's the one on the bottom left, which is evaluative feedback. That's more like the tamer setting, where a person is just saying good job and bad job as the robot is driving. And then there's the traditional reinforcement learning one, where in the bottom right, where it's just learn from its own, from all of your own experience. And the thing in common for all of these approaches was rather than learning, we are taking an existing path planner, global planner, and local planner, like a whole navigation stack. It's the Ross move-based navigation stack. And rather than throwing it out and learning end to end, rather just learning the parameters of that navigation stack. And so, in learning language, you would normally do, you could think of end-to-end learning as trying to learn a motion policy. In contrast to that, what we're learning is a parameter policy. We're sort of putting the classical motion planner itself in the environment and saying that the thing we have control over in our policy is the parameters. And so when we're doing learning from demonstration, we're trying to learn at this parameter space, what are the parameters of our motion planner that lead the planner to look most like the human demonstration. And similarly for the interventions or the evaluative feedback. And so, all of this is, in the end, we have we try to put all these together so that the robot can learn from the traditional reinforcement learning sort of back in the factory when it's got lots of time for experience, and then be put in someone's home and learn from all of these modalities or these different, more creative task specifications of demonstration, intervention, and evaluative feedback in sort of what we call a cycle of learning. And again, I could give a whole talk on the technical details, but again, this is mostly just about the task specification aspects of it. If you're interested, Shueishu put a really nice website together on Apple APPL for adaptive planner parameters learning. The other, then, to completely shift gears, well, not completely, but to shift gears to a different talk, but still in this space of task specification from human interaction. There's a paper that we had in Coral not too long ago with some colleagues. First author was again Brad Knox, the initiator of Tamer. He's actually been involved in all of this work. We introduced what we call the empathic framework for task learning from implicit human feedback, with the idea that that a lot of learning we do as people is through sort of verbal signals or body language. You can sort of learn a lot from a person just by looking at the pose of their body and those kinds of things. You can probably look at this video and guess that the car is probably doing something wrong. The people don't have to say anything or reprogram the car. The car ought to be able to say, don't do that as much. Or you can even look at the pedestrians outside and try to say, is this car making this guy nervous or not? And so this was the sort of the motivation behind learning from implicit human feedback. We introduced a problem called the life problem, or learning from implicit human feedback. We formalize it in the paper, and then introduce a framework called empathic. There's a clever acronym that I forget, but that basically is it was designed to learn from watching a person's facial features, and it has two stages. One is for tasks where we know what the right thing to do is, we just train a camera on a person's face and try to learn a mapping from what a face looks like when the robot's doing the right thing versus what it looks like when the robot's doing the wrong thing, which is actually a lot trickier than you might think. Some people smile when the robot crashes into a wall, and but it's maybe a different kind of smile than when the robot reaches the goal. And then the second phase is you take that learned mapping, that sort of the reaction feature extraction module and the reaction feature vector that we learn, and especially this mapping to reaction features, and then use that as, in some sense, the task specification. Tell the robot, just do the actions that will lead to the most positive facial expressions of your user. And here's the acronym for empathic. It was a evaluative mapping for effective task learning via human implicit cues. And again, interest of time, I won't go into all the technical details of it, but just to say, I think I have a nice, here's a video of what you might be looking at. And the first step of this research was we checked to see whether there's signal in watching faces. And so we did like a human proxy experiment. We would be asking you as a user, can you look at these faces and figure out when the robot did the right thing, when a good thing happened and when a bad thing happened? And it's not easy, it's not straightforward. But in the end, people are able to do it better than random. It's certainly not as good as positive and negative feedback. And we were able to show in this paper that we could get enough signal out of this as the task specification, that we could learn behaviors in a number of different tasks. One was a sort of a control a taxi in an environment domain, and another was a robot sort of recycling sorting domain. I don't know if I can. Well, yeah, this was the taxi domain where you have a taxi that has to navigate around an environment and pick up passengers without running into obstacles. But it was trying to learn what to do just by looking at the people's faces. Here's a relatively easy to read expression, but some of the others are much more difficult. And then the other task, and again, I'm skipping through the details of this. They're all in the paper. But I think, so the other task was sort of a recycling task where we had a robot trying to put objects into different bins, and its only task specification, it didn't know what the objects were, it didn't know what the bins were, it just had to watch a person's facial expression to understand whether it had done something right or wrong and learn from that over time. And then finally, I think I know I'm running out of time, but the last sort of vignette, and this is where all of this sort of does come down to preferences. And so this is Brad Knox again. I'm using his slides here on a recent sort of talk that he gave. But it's really, you can think about all of this human in the loop learning. In the settings that I gave you, it was, a person giving demonstrations, interactions, evaluative feedback. One of the most sort of active and I think interesting task specification languages now is human preferences, where what the way the task is specified is you get pairs of behaviors and you need to indicate which one you prefer. You don't really say good, absolutely, or bad, absolutely. You're just saying among two options, which one is preferable. And that's how RLHF really, sort of works for fine tuning large language models. The human is given a positive, a couple of different outputs. They say which one they prefer. You get a large database of that, and so that ends up being the task specification. There's no reward signal. There's no demonstrations. It's just preferences. And so I'll give you one sort of technical insight that we had here. First, learning from preferences is that there is some preference model, which that says given some reward function, you can say you can say whether one trajectory is preferred to another trajectory. So that's a preference model. And learning from preferences, your goal is to be, if you're given a bunch of pairs of examples of trajectory 1 great is preferable to trajectory 2, can you infer what the actual reward function, the underlying reward function is? And then you could do traditional reinforcement learning with that reinforcement learning. So you want to optimize your estimated reward function to maximize the likelihood of the preferences that were expressed by the person who is expressing them. And so there's a number of different models of preferences. again, due to time, I'll refer you to the papers for a lot of the details. But what we can do is think of it being as a person has a sort of hidden reward function in their head. We show them a bunch of pairs of behaviors and say, which one do you prefer? And then we try to go back and induce and estimate what that reward function was, with the idea that once we know the reward function, we can do learning. Yes, 2 minutes, good. So the sort of traditional way, and actually the way that people have described doing preference model learning, is that they say that the probability that that trajectory one is preferred over trajectory two is if the reward that you get while you follow trajectory one, which is the sequence, the reward for the state action pairs, how much better is that than the reward you would get while following trajectory two? And so it basically, but it turns out, I mean, it seems intuitive, but it turns out that's we think not a great model of what people do when they're giving preferences, in particular, because if you're in this task where you're at the blue dot and you have it's specified, the true reward function is you get a -1 until you get to the goal. These two trajectories would be rated equally. In both cases, you get a -2 over their trajectories, right? They don't, they don't tell you anything about how much progress you're making. And so we proposed a new model called the regret model, which takes into account the estimated sort of value of the start state and the estimated value of the end state, and the difference between them, or the progress that you've made along the way. And the regret of a segment, then we model it as measuring how much it deviates from optimal behavior. So in this case, the same example, you'd be getting -2 for this case, because the optimal behavior is to go towards the goal, and this you'd be getting 0 because you're actually doing an optimal behavior. And if we model that's what people are doing when they say which trajectory they prefer, we can get back to something that's closer to their true reward function. And we analyze this both theoretically and through experiments. This is basically it's ongoing research. Our hypothesis is that we've evaluated is that annotators, when we're asking them for their preferences, give the preferences based on the regret model, and that engineers using fine-tuning are unknowingly applying this regret for preference model, even though in their papers they're often saying that they're using the partial return model. And I know I have to end here, so it turns I'll hopefully use that as a teaser to read the paper and look more at why this matters and why we think this matters. I guess it boils down to the idea that large language models are not actually bandits. There are dialogue is a sequential problem, whereas in the ChatGPT paper they say that they model the environment as if it were a bandit. I can talk more about that offline. I know time is up, so I'll just thank you again for the invitation, for your attention, and pop back up to say this was really the whole theme of this talk was looking at how human in the loop learning, in the how I talked about it as it pertains to robot navigation and learning from implicit feedback and model learning from preferences, can all be thought of as being about how do you specify your task differently from the sort of traditional pure reward function in reinforcement learning. Thank you.
Thank you. Let's give Peter a round of applause. Let's take some questions.
Yes, thank you for that really interesting talk. I guess I just have a more general question about the direction of AI. Do you think that these robots that can learn online, as you're deploying them, what do you think are the prospects of that? I guess just related to safety. And obviously they have a lot of potential. I want to have your thoughts on whether you think that's the way to happen.
Yeah, in some sense, the whole motivation for this line of human in the loop learning is to sort of change from the paradigm where a robot has to learn its behavior in the factory, and then go into your home with a fixed behavior. And then if you want to change it, you have to bring back a programmer or somebody with robot expertise. Change that to a paradigm where you might start there, you might learn from that as for your base behaviors, but then when the robot's deployed in, not my home where I can know how to program the robot, but in my, my mother's home, or in somebody, I don't mean to throw my mother under the bus, but she's not going to program the robot. And so how can she give a signal of what she wants the robot to do without having to to go back to the program level. And so I think we need that. I think it's not now you're right that safety is a concern, and and so you have to be able to do this in a way that is not going to go into sort of horrible spaces of the learning space. But we need, there's no way we're going to be able to train robots to operate correctly in every environment in the factory. They need to be able to do it at deployment time. And this learning from human preferences is all about that.
Thank you.
Thank you. Let's give Peter another round of applause. Thank you.
Thank you.
Okay.